Hello all, I'm Amir and I'm gonna give you a brief presentation about this work, which the title is Online Joint Optimization and Traffic Engineering and Network Update in Software-Defined Wide Area Networks. So this work is quite new, and they claim that they are the first work that propose the algorithms and also the approaches to minimize the total cost, including traffic engineering cost and network update cost in their work. So at first I'm gonna give you some introduction about this work, then I'm gonna talk about the contribution of this work. I mentioned the online optimization framework and online algorithms they proposed in this work. Then I'm going to talk about the strengths and weaknesses of this work, and finally I'm going to show you the results obtained in this work. Traditional, if I want to say what's the problem and what they propose in this work to solve this problem, is that traditional traffic engineering computation only focuses on traffic engineering cost minimization in a single time slot and does not take network update or rerouting costs into consideration. However, frequently switching forwarding rules can lead to route oscillation and degrade application performance. So it is important to exert a joint optimization on traffic engineering and network update costs to minimize the total cost. That is the sum of traffic engineering and network update cost. So because of this, an online joint optimization framework on traffic engineering computation and network update cost is proposed in this work that aims to minimize the total cost, that is the sum of traffic engineering cost and network update cost in the long run. So they claim that they are the first work in this area that consider both traffic engineering cost and network update cost in their optimization problem. So the first contribution of this work is that they propose an online optimization framework to jointly minimize traffic engineering costs and network update costs in the time horizon. The optimization program aims to determine how each flow is escalated at the ingress switch onto the available tunnels and which flow needs to be rerouted such that the network capacity constraints are respected. Which means they consider both here with these two sentences mean that they consider traffic engineering and network update costs in their solution. The second contribution of this work is that they develop a set of provable online algorithms to solve the problem and conduct rigorous competitive and regret analysis. And the third contribution of this work is that they evaluate their proposed algorithm by using two empirical topologies with real data sets. And the evaluation results show that the proposed algorithms in this work reduce the cost on average compared with the state of the art and can perfectly match the theoretical analysis. Okay. So in this paper, to show how traditional approaches in traffic engineering work and how their proposed approach works, they explained a motivating example. So here the upper one, as you can see, is related to traditional traffic engineering approach, and this one shows the proposed approach in this work. Before I'm going to talk about this and how the traffic engineering cost and network update cost calculation works in this example, at first we need to see what's their assumptions. The capacity of each link is 1 unit. There are 3 aggregate flows colored red, blue, and green respectively, and their demands vary with time. The demand of flow A increases from 1 unit at T0 to 2 units at T1 and drops to 1 unit at T2. The demand of flow B keeps the same at T0, T1, and T2, and the demand of flow C increases from 1 unit at T1 to 2 units at T2. So the traditional traffic engineering approach, in traditional traffic engineering approach, they don't consider rerouting cost or network update cost into their calculations. And the only thing that is important for them is to minimize the traffic engineering cost. So by considering this, so now I'm going to talk how they calculate the traffic engineering cost in traditional approach. Here in T0, as you can see here, flow A is going through this path, flow B is going through this path, and flow C going through this path. To calculate the traffic engineering cost, each path has 3 links, and the cost of each link is 1. So the cost of flow A here is 3, flow B is 3, flow C is 3, and traffic engineering cost for T0 is 9. In T1, the demand of flow A increases to 2 units. So as you can see here, we need to send 1 unit of flow A from another path. So since here we only want to, in traditional approach, we only want to minimize the traffic engineering cost, we need to use the shortest path. If we want to reroute that, we say that, yeah, okay, another unit of flow A should be go through this path, not this path. So we choose the shortest path here. So since we choose this one, we need to reroute flow B and we need to reroute flow C. So as you can see here, we do a lot of rerouting because we don't consider network updating cost or rerouting cost in traditional approach. So the only thing matters is to minimize the traffic engineering cost. So here, as you can see here, for flow A, we have 2 paths with 3 hops, and each link has the cost of each link is 1. So as you can see here, the traffic engineering cost for flow A is 6, for flow B and flow C is 3. So the total traffic engineering cost at T1 is 12. And yeah, like before, like T1 and T2, again, the traffic engineering cost is 12, but here the demand of flow A decreases to 1 unit and the demand of flow C increases to 2 units. Here, so now the cost of flow C is 6 and the cost of flow B and flow A is 3. But since we want to compare this approach with the proposed approach in this work, we also consider rerouting, and we also calculate the rerouting cost from T0 to T1. At total, we do 5 rerouting, and the cost of each route is 3. So the routing cost from T0 to T1 is 15, and from T1 to T2 we do 4 rerouting, and the cost is 12. So the total cost for traditional approach is 60. But in their proposed approach in this work, they consider both network cost and network update cost, or the routing cost, and also traffic engineering cost. So from when they want to go from T0 to T1, since they also want to minimize the network update cost or routing cost, they say that, okay, now that the demand of flow A increases to 2 units from T0 to T1, instead of using this path, but if we use this path, we need to reroute all these ones, and this increases the rerouting cost. So instead of that, they say that, okay, we accept that we agree to increase the traffic engineering cost a little in T1, but instead of that, we minimize the routing cost from T0 to T1. And other calculations are like before in the traffic in the previous slide. As you can see here, by using that, at T1, they increase the traffic engineering cost, but instead they reduce their routing cost from T0 to T1 usually. And the traffic total cost here is 45, and for the traditional approach was 60. So we see that their approach is working and is much better than traditional approach. By look at this motivating example. Now to reduce the network updating cost and traffic engineering cost, they proposed some online algorithms to predict the future time slots. So the demand of each fellow in the future time slots. So at first, they proposed a regularization-based algorithm. The demand of each fellow can be accurately predicted in one future time slot using this algorithm. But the problem with this algorithm is that it couldn't benefit from the window size increase. So to solve that problem, they proposed the second and the third algorithm, the receiving horizon control-based algorithm and averaging fixed horizon control-based algorithm, which allow the network operators to predict the fellow demand in multiple future time slots with bounded prediction errors. So the strength of this work is that the main strength is that they are the first work that consider both traffic engineering and network update cost in their optimization problem. They propose a novel online optimization framework for jointly minimizing traffic engineering cost and network update cost in the time horizon. They develop a set of provable online algorithms and conduct rigorous competitive and regret analysis. Their evaluation results show that their proposed algorithms work much better than the other algorithms in other books. And also, they use different lemmas and theorems in their work to show the authenticity of their proposed formulas and algorithms, which makes this work more reliable. So since this is quite a new work, and it was published in July 2021, and there is no newer work using the similar idea that we can compare and see the weaknesses of this work, it's hard to talk about the weaknesses of this work. But if I want to mention some weaknesses, I can say that they modified the algorithms proposed in other works to make them comparable with their algorithms. Therefore, these modifications may affect the performance of other algorithms. And maybe this makes their evaluation not that reliable. Another weakness is that RS4 algorithm cannot benefit the window size increase, especially when the number of targets is more than one. And the evaluation and results, if I talk about them, is that to implement that, they consider two realistic topologies and traffic matrices of them are obtained from Gent topology and Nobel Germany topology. I hope I pronounced this one correctly. And the evaluation results show that RA, RHC, and AFHC can reduce 12.1, 12.3, and 15.4% cost on average compared to the state of art and can perfectly match historical analysis. And they evaluate their algorithms with two other schemes, SOL, the SDN application optimization APIs, and OPT, offline optimum, that assumes all future inputs are known as a priori. And as you can see here in the results, AFHC performs best both AFHC performs best in both topologies, whose cost is 14.4% larger the OPT on average. And this is because AFHC is an average of several future time steps using look-ahead values. And they use different routing approaches to generate the tunnel, and they generate the flow based on those tunnels. As you can see here, they use KSP, ECMP, Oblivious, and EDSKP routing approaches to generate the tunnels. So to briefly overview what I talked about is that an online optimization framework for jointly minimizing TE cost and network update cost in the time horizon is proposed in this work. Set up provable online algorithms and conduct rigorous competitive and regret analysis of developed in this work. And finally, extensive evaluations using two empirical topologies with real data set demonstrated that their online algorithms can decrease the total cost and close to the offline optimum. For the future works, I think their novel idea has a huge impact on future works, because if you want to do some work in the future, you need to consider both network update cost and TE cost into consideration. And the future works need to consider these two parameters in their research to make their works more reliable and comparable. And also we, in our project for this course, we use the different learning approaches to speed up routing in traffic engineering. And to minimize the cost, we consider the total cost, like the network update cost and also the traffic engineering cost in this work. And this paper is one of the base papers of all for the project of this course. So thanks a lot for listening to my presentation. And if you have any question, you can ask me on discussion on Brightest List. Okay, thanks a lot.